So continuing on, I'm just going to do a quick little bit of a review. So we had done some rational functions last year in pre-calc 20. We're doing more complex ones in pre-calc 30. Y-intercepts happen when our x's are all set to be 0. We have three types of zeros. A 0 in the numerator means an x-intercept. A 0 in the denominator means a vertical asymptote. And a 0 in the numerator and denominator actually produces a hole. Again, the entire reason is because you can't have an x-intercept and a vertical asymptote at the same time. We've done some stuff with our sine analysis. We're going to be doing quite a bit more in our more examples later on. But where we had left off is talking about horizontal asymptotes. So again, horizontal asymptotes are not really quite as strong as vertical asymptotes. It talks about a calculus concept which talks about limits to infinity and negative infinity. The first rule, and yes, these, what I did neglect to say, is you do have to memorize these rules. Traditionally, only do a lot of quizzing on 1 and 2, but you still will have to know what 3 is. So the first rule is when the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will be the line y equals 0. So in the case of 1 over x, the degree of our numerator will be 0 because there are no x's. Or in other words, x to the power of 0 is just 1, whereas our denominator of x has a power of 1. And since the numerator is less than the degree than the denominator, and usually how I denote that is the degree of the numerator is less than the degree of the denominator. Our horizontal asymptote will just be y equals 0. By using our graphing calculators, we can see that this is what our graph would actually look like. The second rule is that when the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the line taken by dividing the leading coefficients. So if we look at what our leading coefficients are in here, because our degree of our numerator is equal to the degree of our denominator, all we have to do is divide our leading coefficients. So our leading coefficient in front of our numerator is 3. Our leading coefficient in front of our denominator is 1. So our horizontal asymptote is actually going to be the line y equals 3. When we use our graphing calculators, please take the time to do this. I'm just going to actually make some nice lines here, because those were not anywhere close. All right, so pause the video, take the time, actually graph it. Our graph looks something like this. Let's see. Goes up and down. And there. So that's what our graph actually somewhat looks like. I'm just going to move that down a little bit to make it a little more realistic. If you were to check one more thing, for example, if you were to actually graph the line y equals 3 as well in here, so again, using your graph calculator, type in y equals 3, you would see that there will be a line right below those two upper L's. That will be what our horizontal asymptote is. Of course, at the same time, we know what our vertical asymptotes are, because we just have to find out where does our denominator equal 0, and our denominator would factor into an x plus 2. and x minus 2. That's why we have vertical asymptotes of -2 and +2. And you could actually graph those on your graphing calculator as well. So if the degree of the numerator is less than the degree of the denominator, it's y equals 0. If they're equal, you divide the leading coefficients. And the harder one to do is actually tying back to our first unit. It's when the degree of the numerator is greater than the degree of the denominator. So the degree of the numerator is greater than the degree of the denominator. The horizontal asymptote is oblique or slanted, and it's equal to the equation when the numerator is divided by the denominator. In other words, we actually have to do a little bit of long division. So like most things I like doing is I like bringing back those skills. It doesn't hurt to practice things that we've already done. So we're going to take x cubed and divide it by x squared, subtract x, subtract 12. So our first step to long division is finding what do we have to multiply x squared by to give us x cubed? Well, that's going to be x. And yes, I'm putting it over there a bit. Actually, I should probably move it over a little bit more. That way I have x multiplied by x squared, giving me x cubed. When I do a subtraction, I'm okay. Then x multiplied by negative x. Well, that's going to be a negative x squared. And x by negative 12 is a negative 12x. What do we have up here? Well, we have 0x squareds, 0x's. So that'll help us with our subtraction. Just going to make that look like a 3. So x cubed over x cubed, or subtracting x cubed, gone. 0 subtracting negative x. Well, that's going to be a 1x squared. Oh, sorry, yeah, negative x squared. 0 subtracting negative 12. Well, that's going to be a positive 12x. Then we go back again. X squared multiplied by what will give us x squared? The answer will be positive 1. So then we go back to positive 1 multiplied by x squared, positive 1 by negative x, positive 1 by negative 12. We're going to subtract this one. X squareds are gone. 12 subtracting negative 1 is 13x. And we'd have 0 being brought down. 0 subtracting negative 12 would be a positive 12. What we need to look for is just this dividend. Just that thing that got up at the top. That is actually going to be our horizontal asymptote. Now, I say horizontal in this case as something in quotations. It's not really horizontal, it's going to be slanted because it is the equation y equals x plus 1, which is a linear function with y-intercept of 1 and a slope of 1 over 1. So let's take a look at what the graph here does. You type, so take the time, plug it into your graphing calculator, and you'll see something like this. Our graph will do something like this. It's going to go about like this, then it'll actually just give me a second. I'm just going to plug it into my graphing calculator. That's a good thing I did, because this is actually way more like that. You'll see, that's probably what you see originally, but we are going to graph the entire function. First thing that you'll note is that you have a vertical asymptote of, should be -3. So that would be at -3. You also have a vertical asymptote at +4. Why? Because this denominator would factor into an x subtract 4, x add 3, and setting those equals 0 would be -3 and +4. The last bit of the graph, though, is actually a little bit higher up. It's a little bit over your 10 by 10 grid. So if you zoom out, kind of looks like that. Now I want you to graph the line y equals x add 1. When you graph that line, y equals x plus 1, is just like that. You are actually having your function spoon with your asymptotes. Of course, when I draw my horizontal asymptote, I do make sure that it is dashed, because it is not an actual line, it is completely imaginary. Ta-da. Alrighty, now that we've talked about horizontal asymptotes, we're going to go back a page. We're going to finish off these questions. So the last bit of our notes here, we had already done our x-intercepts, our y-intercepts, our vertical asymptotes. We had done our sign analysis. But the last thing we need to do is identify what our horizontal asymptote is. So let's apply our 3 rules. In this question, we see that our degrees are both equal. When our degrees are equal, sorry, this should not be, that's not a smiley face, that's just an arrow. We have to divide our leading coefficients. So we're going to have a horizontal asymptote of y equals 4 here. In this one, our numerator has a degree of 0. So our degree of our numerator is less than the degree of the denominator. That means our horizontal asymptote is y equals 0. So our horizontal asymptote is y equals 0. Let's take each of these one at a time, and let's graph it. The first thing that I usually like doing is identifying what my horizontals and vertical asymptotes are. So I already know that my vertical asymptote is at 2, and our horizontal is at 4. Now that's not x equals 4, that's y equals 4. Horizontal asymptote is right there. Our vertical asymptote is at 2, at x equals 2. So that puts us right there. We're also able to find out exactly what our x-intercept is. Our x-intercept is 5/4, or 1.25. 1.25 puts us about right there. Our y-intercept, it says, is 2.5, or 5/2. 2.5 works out a little bit nicer for graphing. The last step that we need to do is go back to our sign analysis. So our sign analysis says that on the left-hand side of 5/4, so that x-intercept, where it equals 0, our graph has to be positive. Well, what does it mean to be positive? Positive means above the x-axis. So we're going to ask the question of how far above the x-axis? The rule of thumb that you can generally follow is you want to be above the x-axis, but if our horizontal asymptote is already above there, well, we're just going to stay below it. Our graph is going to kind of just spoon with that horizontal asymptote right there. Oh, that's 5/4. In between 5/4 and 2, it's negative, which means it's going to be below the x-axis. And it spoons with that vertical asymptote. It does take practice to realize and see where and how these graphs interpret. At the same time, you do have your graphing technology to help you be able to get some of it. Our vertical asymptote is at 2. We've already sketched that out. Now, we just have to deal with greater than 2. Well, it's going to be positive. Now, yes, positive does mean above the x-axis. In this perspective, it's also going to make more sense to stay above our horizontal asymptote as well. The reason for it is it's very hard to stay above the x-axis if we're trying to stay close to our asymptotes like this. So don't sketch this, because right here it's saying that we're below, but that's not what we're doing. We have to stay above, and we do want to try and spoon with the asymptotes a bit. And if you use that rule, it also makes this part make more sense as well. There may be sometimes, oh, sorry, there's my arrows. There may be sometimes that the graph will actually go above, but it'll kind of just keep on wavering over back and forth over your horizontal asymptote. Our next example here, this is actually an exact question that we would have done in pre-calc 20. The horizontal asymptote is y = 0. Our vertical asymptotes says here is 3 and -2. Even in our sine analysis, is 3 and -2. There's a 3. There's the -2. We don't have any x-intercepts. Well, that makes sense, especially since our horizontal asymptote is literally right along our x-axis. We're not going to really touch this one in this case. Or maybe sometimes we will, but this one, not so much. Y-intercept is -1/6, so -0.1666666. We'll put it about right there. Our sine analysis, this positive, oh, that number is -2. This number is 3. All right, so on the left-hand side of -2, we're going to be positive. Well, the only way we can be close to those asymptotes and still be positive will be like this. In between the -2 and the +3, it says negative. Well, the only way we can stay close to those asymptotes is like that. And positive on the right-hand side of 3, well, that means this. I encourage you to type these into your graphing calculators and check them out. Make sure that they actually work. Once you've done that, yeah, they look good. All right, so now we can actually get into some hard questions. When I say hard questions, I mean examples. the good news is we're not going to be doing anything different. We're just going to practice those same skills over and over. So the first thing we're going to do is identify the following characteristics for y equals x squared subtract 25 divided by x squared plus 6x plus 9. We're going to identify our x-intercepts, our vertical asymptotes, any points of discontinuity that we might have, which are holes, our y-intercept, and our horizontal asymptote. Perform a sine analysis, and we're going to graph it. First step, this is hard to graph. Yes, we can put it straight into our graphic calculator, and we'd be set. But I want you to be able to show all of these steps. And I'm going to show you how we do all of those steps. The first thing is we're going to factor the numerator and denominator. The numerator is a difference of squares. X add 5 and x subtract 5. Our denominator is a perfect trinomial square, which just means that, my phrasing is product of 9, sum of 6. Well, that's positive 3 and positive 3. And that will help us do the rest. So our first thing that we're going to do is our x-intercepts. Well, our x-intercepts only occur in our numerator. So where does x plus 5 and x minus 5 equal 0? At positive and negative 5. This one at negative 5, and this one at positive 5. Our vertical asymptotes are where the denominator equals 0. Well, that's only going to be once, and that's negative 3. Points of discontinuity only happen when you have the same factor in your numerator and your denominator. This one, there are no factors in common, so there's none. Our y-intercept. This one can be tricky, especially with our factored form, but our y-intercept always occurs when all of our x's equal 0. So if we were to plug 0 into here, well, that's 0 squared. Subtract 25 will be a negative 25. And our denominator here, 0 squared, add 6 times 0, well, that's all still 0. Add 9 is 9. I'm just going to convert this into a mixed fraction because it's easier to be able to graph it nicely. Of course, I know from here now, that would be negative 2.7 repeated. Fifth step is determining what our horizontal asymptote would be. So we're going to go back to these rules. Degree of the numerator and degree of denominators are all that we have to do. So the degree of the numerator, if it's less than, y equals 0. If they're equal, we have to divide the leading coefficients. And if the numerator is greater than the denominator, we have to do some long division. Find out what is that dividend. So here, we're going to go back to the original question because it's easier to look at. Well, we can see that the degrees are the same. So we're going to divide the leading coefficients. 1 divided by 1 is 1. Now we're going to perform a sine analysis and graph. So sine analysis means we're going to put all of our zeros, which means the zeros of our numerator and our denominator, across the top. Well, those are these. Put them in order from left to right, which means we have negative 5, negative 3, and positive 5. Then we have to put all of our factors down the left-hand side. It is the easiest to keep your numerators over your denominators. And yes, I do encourage you to write each and every single one. Even though this does come out as x plus 3 squared, it's just going to make your life easier, especially doing your sine analysis. So there's our 0 there, there's our 0 there, and these two are zeros. Plug anything less than -5 in, that's going to be negative. Anything greater, that one's going to be positive. I know the rest of this is going to be pretty nice and basic. Now I am still plugging these numbers in my head. Just be careful. I think I like adding in every so often if it was like 5 subtract x, which is different. So be careful. The good news is on these last two, they're the exact same, so they're going to have the exact same characteristics. Now let's actually do the sign analysis part. 4 negatives is positive. A 0 and 3 negatives, well, where is the 0? That 0 is in the numerator. So it's 0. A positive and 3 negatives is negative. Positive, negative, and 2 zeros, well, where are those zeros? They're in the denominator, which means it's a vertical asymptote. 3 positives and 1 negative is negative. Positive 0 and 2 positives, where is the 0? This x subtract 5 is in the numerator, which means it's 0. And then positive. We can just go step by step, identify our different parts. X-intercepts, a positive 5 and negative 5. Positive 5, negative 5. Our vertical asymptote, x equals -3. So -3. Don't have any holes. Our y-intercept is -2.7. Repeated. We'll put that about right there. And then our horizontal asymptote is y equals 1. So y equals 1. Yeah, right there. So the rest of the question is asking, how do we do our sign analysis? We're positive on the left-hand side of -5. The only way that we can be close to an asymptote and be positive is like that. Usually I start from the left. It makes things a lot easier to graph. In between -5 and -3 goes negative. The only way I can stay close to those asymptotes and actually spoon with them is like that. In between -3 and positive 5, it's negative. The only way I can stay close is like this. I have to go through my y-intercept, go to 5, and then I know that the last part of it says it goes positive. Plug the original question into your graphing calculator, and it should be pretty darn close. By graphing it, though, you will see one thing that's different. And I'm fine with you having this, but what you'll actually see is this graph still follows that same path, crosses at -5, but actually goes above that horizontal asymptote. But if you pay attention later, keep on scrolling over, it does go right back to going along that horizontal asymptote. That is why I say that horizontal asymptotes are not quite as strong as vertical asymptotes. But for our purposes in pre-calc 30, this is perfectly fine with me. You wouldn't have to make this change, but it would be something that's fun to note. In calculus 30, you'll be talking about concavity, and you'll be able to actually make these sketches even more accurate. Right. But one more question. So again, this is perfectly fine with me. It shows me your skills. With all of our pre-calc skills, you wouldn't really know that it does go above. And that's fine. Alrighty. So let's do this one. Still identify the same characteristics over and over. Factor the numerator, factor the denominator. Well, the numerator would factor into an x squared and an x subtract 5. The denominator would factor into an x and an x add 5. Our x-intercepts happen in our numerator. So that would be x squared equals 0 at 0, x subtract 5 equals 0 at 5. Now, you might notice one thing already. I'm getting to it. Vertical asymptotes, well, that would be at x equals 0 and negative 5. Points of discontinuity. This one is a new one. And it's hard, it will be very hard to see in the actual graph of it. Points of discontinuity, basically, are there any repeats between our x-intercepts and our vertical asymptotes? Yes. So what I want you to do on assignments is either erase this or cross it off. It is not an x-intercept. It is not a vertical asymptote. It is a point of discontinuity. The entire reason that it's a point of discontinuity is because you can't have an x-intercept actually be crossing something, but not cross it with a vertical asymptote. Our y-intercepts happen when x is equal to 0. Well, plugging all these zeros in means that we'd actually have a 0 over 0 case, which is the exact premise behind this point of discontinuity. We're actually not going to have any y-intercept in this one. But we are going to have a horizontal asymptote. Our degree of our numerator is greater than the degree of the denominator. In order for us to do this, that means we're going to have to do some long division. And should be x squared subtracting 5x. Make sure I wrote that down correctly. Oh, signs are switched. I didn't have those. Make sure that that's right. Yep. All right. Now I can long divide. X squared multiplied by what will give us an x cubed? Oh, that's an x. So x by x squared is x cubed. X by a positive 5x will be a positive 5x squared. Subtract it off. Negative 5 subtracting 5, negative 10x squared. Now we have to ask ourselves, x squared multiplied by what gives us a negative 10x squared? It'd be negative 10. We have 0 x's. We'll have to bring that one down. So the negative 10 by x squared would be a negative 10x squared. Negative 10 by a positive 5x would be a negative 50x. Subtract it off. Negative 10 subtracting negative 10. Well, that's nothing. And 0 subtracting negative 50 is 50. I can't take x squared and multiply by anything to give me 50x. So my horizontal asymptote, and writing that in red, is y equals x subtract 10. All right, so we can go to our sine analysis. it is easiest to do to actually have all of our factors, which means our factored version. So I'll put my factored version, my x squared, my x subtract 5. Those are from the numerator, right? Yes. Denominator is an x and an x add 5. The zeros of the numerator is 5, 0 at the denominator, -5. Our point of discontinuity is at 0. So -5, 0, and +5. Plug in our zeros. That'll be the easiest thing to do. You plug any number into an x squared, it'll always turn positive. This is one reason why you have to be careful. You can't just assume that the left-hand side is always going to be negative and the right-hand side is always going to be positive. Not always the case. Alrighty. This one, yeah. This one will be the negatives and positives. This one, negatives and positives. And then we do our sign analysis. Positive and 3 negatives, negative, positive, 2 negatives, and a 0. Where is the 0? It's in the denominator. It's a vertical asymptote. And that is exactly what's identified in by I. Positive, 2 negatives, and positive. Oh, that's positive. 0, negative, 0, positive. Where are the zeros? This one's in the numerator. This one's in the denominator. That's a whole. Maybe it might make sense to add in a, I mean, if you have something kind of colored, actually no, that's gonna make things really ugly. Never mind. But forget I said it, something. 3 positives and negative, it's negative. 3 positives is 0. The 0 is in the numerator. And 4 positives. Alrighty. Let's hit her up. X-intercept, 5. Vertical asymptote, -5. A hard one to do though is graphing the point of discontinuity, because we're going to need to know where it is. So for this one, we're going to need to start graphing first. Now we don't have any y-intercepts because of this. Now, actually that does kind of help a little bit, but we don't need to know that. Horizontal asymptote is y equals x subtract 10, which means it's a y-intercept of 10 and a slope of 1 over 1. Now these graphs do continue on indefinitely. So let's start with the graph. Negative on the left-hand side of -5. Well, the only way we can be negative and still be close to our asymptotes will be here. On this one, we are positive in between -5 and 0. Well, the only way that we can be positive is here. Now we're going to have to be really close to here. That's trying to get us closer to that horizontal asymptote. Then we get a hole. Well, in this case, as we're graphing, I want you to actually draw a hole. Depends on the situation. So there may be cases where you're going to have asymptotes and you might be graphing here and then, oh, hole, and then you just keep on going. But That's for different ones. In between 0 and 5, we go negative. X-intercept and positive. Plug it in. I'm fine with you using a little bit of help. The holes, though, are going to be really careful. It just depends on where your graph is. So if this graph had a hole at 7, well, as we're graphing it, we would just put our hole at 7. Just as we're graphing, oh, we're at 7, hole. I'm not too much of a stickler of exactly where it is, but it does have to be close. Alrighty. Have some fun with the assignment.